Can Einstein's theory of relativity be wrong? Find out as we explore Euclid, a new space telescope studying dark energy and dark matter.
3, 2, 1, engine full power.
Welcome to your space journey, where we venture into the future of space exploration. Your journey begins now.
Hello, thanks for joining me today for your space journey. I'm your host, Chuck, and today we're going to dive into Euclid, a new space telescope from ESA. Since 2012, Giuseppe Racca has been responsible for the Euclid mission as a project manager. Euclid is a space-based optical near-infrared survey mission from ESA designed to investigate the nature of dark energy, dark matter, and gravity by observing their signatures on the geometry of the universe and on the formation of large structures over cosmological timescales. Euclid will use two main techniques in the detection of the signature of dark matter and energy: weak gravitational lensing and galaxy clustering. The spacecraft is scheduled for a launch date in 2023 and is designed for 6 years of nominal survey operations.
Your space journey.
Giuseppe, thank you so much for joining me today.
Thank you. Thanks to you.
Well, it's a pleasure to have you here. And I was wondering, just to start off, this is obviously about ESA's mission, Euclid. Can you give just the big picture, high-level view of what Euclid is?
Wow. Yeah, it's Euclid is actually a telescope in itself. It's just a telescope. It's a visual and near-infrared telescope. So it looks at what we see, the visible and in the near-infrared that our eyes cannot see, but not too far away in the infrared, not like JWST, for example. It's just what we call the near-infrared. And it's a telescope. It's a fairly large telescope, but not even the largest telescope that one has. Indeed, the JWST is a larger telescope. Even Hubble Space Telescope has a primary mirror, which is twice as much the one of Euclid. But it's still a fairly large telescope to be launched in space. And the peculiarity of this is basically that it has to, as objective, has to address cosmology. It doesn't really make a particular observation to one particular part of the sky or one particular feature, but as a whole, the entire universe. So this is the peculiarity. And dark matter and dark energy being the two things which make up most of the universe, it's indeed addressing dark energy and dark matter.
Excellent. We'll definitely talk more about that in a little bit. But first, I wanted to just talk about sort of your role. You're senior project manager for it.
Yeah.
Can you tell us more about your role and your responsibilities?
Yeah, project manager. I'm the project manager, as you correctly say. In ESA, we have in the European Space Agency, where I work, the responsible person for a mission until it is launched and until it has demonstrated in orbit is what is called the project manager. So the overall responsibility for the mission delegated from the Directorate of Science. Director of Science is responsible for the mission, all the science missions, and he delegates this responsibility to someone like me that is a project manager until the launch takes place and the first 3 months for what we call the mission commissioning. After that, the responsibility is handed over to another one that is called mission manager. So it's called the project manager and then mission manager, but that's basically is the responsibility for the mission. So in a way, I'm responsible for the whole mission. I have to take care of all aspects. Of course, I have a team and I'm supported by experts in various areas. There is also the various scientific support from various sides, including a project scientist and various other technical disciplines, etc.
Wow, you certainly have a lot on your plate. I can imagine just seeing the big picture of all the different disciplines and people you have to work with on that. Now, Giuseppe, if I have this right, you've been with ESA for more than 30 years. I was just wondering if you can tell us, where did your passion for space come from?
But actually, I've studied nuclear physics myself and nuclear engineering, and I have had a passion for physics in general. That has always been my passion. And at the time, I have let's say I finished university, and I was still doing some research in university. It was not really the right time. I wouldn't put it like that, but it was a very good time for space at the time. I was even involved a little bit at the very beginning of the Large Hadron Facility being built up in Geneva. My professor was one of the principal investigators or something like that.
Mm-hmm.
But space was booming at the time in the early 80s. It seemed that everything was let's say bringing me there, and I had an opportunity to start working for space. Don't want to disappoint you, but I was not a passionate for space at the beginning. It was more for physics and
That's okay.
Yeah. But then I became attracted by space because it was really a booming thing. Let's say everyone wanted to go to space. We started having the first astronauts in Europe. For, let's say, in America, of course, from the Apollo time, there were already a lot of astronauts. But in Europe, it was just about starting, because there was Space Lab, that was called,
Mm-hmm.
that was starting, and then there was a lot of activities. So then I started there, and I continued in that area. And now, as you correctly say, I'm actually in ESA for more than 35 years now. Wow. So it's a long time. And nearly always worked in the science program, except at the very beginning. So I have seen many science missions and gone through very many exciting projects, and I like them all, and I'm very passionate for space now.
Yeah, and that's fantastic, and I really respect the interest in physics. I'm a big physics fan as well. Now going back to Euclid, it's one of those features where the most important, you're studying sort of the dark side of the universe, and you're studying dark energy, dark matter. In a general sense, can you give let's dive into dark matter? Like, some of our audience might not know, what is dark matter? What is dark energy? Can you tell us just a little bit more about how you would describe that?
Yeah, actually, it's not even very correct to call dark energy dark matter, to be honest. It's actually, one should better call it invisible, because it's actually something that we don't see. Let's say we don't see with not only our own eyes, which only see a part of the electromagnetic spectrum, but we also don't see it in any in any wavelength, let's say in any type of light. We don't see it, and this matter energy is not absorbing either. So then in that sense, it's something that does not interact with the electromagnetic forces. Let's say you don't see it, and they don't absorb. But we know that it exists. Why do we know that it exists? And this is slightly different from dark energy and dark matter. Because for dark matter, we know that it exists because we see the gravitational effect of dark matter on its surrounding. So we don't see it from light emitted or absorbed, but we see that it should be there. Otherwise, all other things around it would not rotate the way they do. This has been already discovered many, many years ago, in the early 19th century, where it was seen that, let's say, the rotation of the galaxies or the rotation of some, let's say, clusters of galaxies were as if there was much more mass than what there is inside. Let's say what you can see, you see a certain amount of mass, and then you would expect that the galaxy, for example, rotate with a certain speed, and instead you measure the speed, and you see that it does not rotate with that speed, but it rotates with higher speed, which it means that it is actually higher mass inside and distributed somehow. So then you understand that, yeah, there must be more mass, and this mass is called dark matter. Let's say dark because I don't see it and does not absorb, but it must exist because it attracts. So gravity wise, it exists, electromagnetic wise seem not to exist, but it must exist. So that's why for the dark matter must consist of something which does not interact in an electromagnetic way. Let's say the forces that it uses, it must be something else. It must be weakly interacting, let's say, that in a way like neutrino, for example, they also do not interact with light, not much. And then this must be something like that, which, however, has its own well-established mass, actually 4 or 5 times the mass of the normal matter. So it's not even little. I mean, it's a lot. It's actually quite a lot.
I know Euclid has some tremendous instrumentation on this, and I'm just kind of wondering, how is it going to measure that? Is it sort of looking at redshifting? How is it going to fulfill that sort of scientific investigation?
Yeah, indeed, we have instrumentation on board, as you say, and this instrumentation is really made not to see dark energy and dark matter, because we just said that you cannot see it. So what we are actually observing is the normal, let's say, big structures of the universe. Let's say what we are interested in, basically we say, what we need is to observe most of the universe, because if you want to talk about cosmology, you cannot watch that little bit of the universe here and there, etc. You need to watch most of it, as much as you can. What can you observe from the ground? What can you observe from space? From ground, you are limited to many things. Let's say you have the atmosphere in between. You can only look on one side. On the other side of the Earth, you cannot look. Let's say wherever you are, you look on one side. Instead, going into space already allows you to look all around. But even all around is not that correct, because we are inside our solar system, and the solar system is inside our own galaxy, and therefore what we have around is actually full of local stuff. We are not really looking at the universe itself. Therefore, what Euclid will be doing will be looking outside our own galaxy, let's say really towards the north and south galactic poles, let's say galactic area in the north and the south, outside our own solar system, to try to look as much as possible outside our own local universe. And this is already about 40% of the universe. Let's say if you remove all this, let's say out of the 100%, you already have 60% of the area that is not really accessible, because you have stars in between, you have dust, you have other things. So already, just to give an idea, that looking at the entire universe means about 40%. So, and that's what we are trying to look at. Now, what do we look at? We look at all the big structures which are outside our own galaxy, which means other galaxies, which means a cluster of galaxies, grouping of galaxies, let's say all the big structures which make up the universe. We are not, of course, not interested in various planets around various stars in various galaxies, because this is much too tiny to make really in the budget of the mass budget of the universe. So what we want is to really look at the big structures. So by looking at this big structure, we can see, we can really make a map of the universe, of all the stuff that there is in the universe. This is one thing. We can also do another thing, for example, is to look at the shape of all these galaxies. The shape of the galaxies is deformed by the matter that there is between the source of the galaxy and the observer, that is us. This distortion is made by all the dark matter and normal matter that there is, and is also influenced by dark energy, by the way, the combination of both. So looking at this shape, it's very, very difficult, because, first of all, because we don't know what is the original shape of that galaxy. And also because the deformation due to this is called weak lensing, weak gravitational lensing. This deformation is tiny. So then one of the main characteristics of Euclid is that it has to be absolutely accurate in the measurement, because Otherwise, if you're not accurate, if you are dominated by some errors, some systematic errors, you cannot really distinguish this deformation that is due to this weak lengthening from any other effect. So then Euclid, therefore, one of the things that it does, it would look at few billion galaxies and measure the shape, very accurately the shape. The precision is given by the fact that you measure so many galaxies. Let's say by measuring billion of galaxies, you have the precision. But the accuracy, you still don't have it unless you have a really perfect instrument. And when people ask me how to define Euclid, I say it's a perfect telescope, because as perfect as we could make it, and it has to be perfect, because otherwise you cannot really make that accurate measurement. That's one thing. And the other one is the one thing that you also mentioned is the redshift measurement. We are also doing that on the same big structure, galaxy and galaxy clusters. We are also measuring the redshift, because of course the redshift is the speed that these are recessing with us from us, and we measure in H alpha, which is one line of emission, which is a line that is very bright in structure in stars which are young stars, let's say, and this is not visible from ground at certain redshift, and it is only visible from space. So this is another advantage. And once you have the receding velocity of all these galaxies and you put them into this model, you can actually find the distance of it's a way of finding the distance of these galaxies, which is related to the Hubble's constant. And therefore, we can have a kind of 3D position and distribution of all the big structures of this 40% of the universe. Having that, it constrains a lot what is the dark energy and the dark matter content, let's say, and also it gives more details. For example, concerning dark matter, it gives you really a full distribution in the universe of the dark matter. For example, is the dark matter concentrated inside a galaxy, like for example a black hole or something like that, or it is something which goes all around the galaxies or in between galaxies? And for dark energy, for example, one of the big questions, which I was hinting a little bit before, is it really a constant, as we said, let's say a constant density or not, or has some variation? Because there are fields, for example, one example that to me at least, which I'm not a theoretical cosmologist at all, but I always found interesting the fact that we have the inflation very early in the universe. There is this inflationary period where the universe hugely increased in size after the Big Bang. And that was also a field, a scalar field, that made this happening. This one, it's something which happens much, much later, let's say 10 billion years later, roughly. And it looks like something like that, but that one stopped. So it did not continue. So understanding the dynamic of the dark energy field is something very important, because it may give to the theoretical cosmology, the theoretical physics, some more hints. And Euclid is really measuring that as well. A third thing is also that, as let's say, the name of Euclid is actually after Euclid from Alexandria, that is the father of geometry, with these elements that he wrote, which is still considered one of the best treatises on geometry still today, let's say. I tried to read it. It's not that easy, but anyway. Geometry is very important because, according to general relativity, geometry of space-time is what rules let's say, what matters actually rules the geometry of space-time. Let's say dominates and makes it curving and bending, etc. This strict relationship between geometry and matter, if it is correct, what general relativity states, let's say this type of relationship, you have this problem. Let's say you have the fact that there must be some dark energy, but there is also a possibility that in reality, general relativity is not the right interpretation of this at very large scale. We know that general relativity works very well for at the level of the solar system, also larger than the solar system, but at the level of universe size, we don't know. So it could also be that at the level of few gigaparsecs, that is really big part of the universe, this does not work. And in our observation, we have ways of discerning this, because you by looking at certain level of the scale of the universe, you can distinguish if it is an effect due to general relativity or due to this to something else, let's say to the dark energy and general relativity, or to another theory of gravity which better describes this relationship.
Giuseppe, if I may, I just have one more question for you. One more quick question. What excites you the most about the Euclid mission?
But what to me, it's two things. To say, one is the one I was just saying. If by any chance it would be discovered that general relativity is not the right theory of gravity, for me this is really a huge discovery. And the second thing, which instead more and more I like, is the fact that by doing this mission, let's say we are a very practical mission. Let's say we just observe things and we bring data down. And the amount of data we are bringing, a few days ago, I just made a check of how much data we bring to ground with respect to Hubble. Now, I don't want to say something wrong, but I think we have let's say Euclid will generate in the first few days, if I'm not wrong, as much data that Hubble has produced in 32 years, without getting, let's say, without trying to play down Hubble at all, of course. Right. Sure. But just to give you an idea of the amount of data that will be amount of observational data. It's not invented data. Observational data with high accuracy, high quality observational data. So this will generate a database for extragalactic astronomy, which is really a gold mine for the future.
Giuseppe, this is incredible. We're so excited about the mission, and I want to just really appreciate you and your team. Congratulations so far for it. We're looking forward to the results for sure. Giuseppe, thank you so much for taking time out of your busy schedule to join us today. Really appreciate it.
Thank you. Thanks to you for the interest.
Your space journey.
Well, I really enjoyed my conversation with Giuseppe today. Hope you did too. And I'm excited about ESA's upcoming Euclid mission. If you'd like to learn more, just go to their website at esa.int. I want to thank Giuseppe for joining me today. I want to thank you for joining me as well. Again, if you could do me a small favor and share this episode with a friend, I'd certainly appreciate it. Thanks so much for joining me. I'll see you next time. God bless.